simplified form is how you're going to get your code into a container image. We'll have a bit of a certain focus on Java-based code, but a lot of the things that I'm going to show today will also be applicable for non-Java applications. So I guess most of you have gotten in touch with containers and heard about Docker and the options of like a Docker file to build a container image. We will also see today that a Docker file is not always the same as a Docker file. There are different ways to do that. There are a lot of configuration options. We're going to look into this. Next to Docker files, there are several other possibilities to build container images.
Toolkit, right? To provide developers with a toolkit to build these distributed applications. And we want to do this in a very specific way because that's, it's been done before. A lot of people are trying to do that, and that's precisely it. Developers are a very diverse group of people, and not everyone wants to build their applications the same way. And although there's a consensus that, okay, if I'm building an application that's going to be available online anyway, it needs to be this distributed system, really.
The container image, really. A little bit of history here before we go on. So up until fairly recently, and when I say fairly recently, I mean 10 years back, 2014-ish, there was only one container image that was very popular that was used by all the tooling. And back then, predominantly, it was Docker. And the image format was called Docker image format. And with the emergence of all the container tooling that was happening around 2015, there was a need for standardization of container images, right? And so this project called Open Container Initiative was established. This is now a Linux Foundation project. And it aims to standardize all things containers, right? So naturally, it created a standard for images, which we call the image specification. In short, it's known as image spec, OCI image spec. And so for the sake of this presentation,
dann bekommt das ganze Leben und Arbeitsspeicher, CPU, bla bla. Cool. Und ja, wo kommt dieses komische Layer her? Dockerfile. Haben wahrscheinlich fast alle schon mal gesehen. Ist für, glaube ich, kaum wen was Neues. Ich habe jetzt mal genau das Demo-Beispiel auch wieder aus dem Docker-Doku mir rausgepickt, weil es einfach ein paar schöne Sachen nimmt. Es gibt dieses eine Schlüsselwort ist immer drin, Form. Das ist, von welchem Image fange ich an. Es kann auch ein Empty Image sein, alles cool. Ich setze ein Label rein, standardmäßig ist meistens alles drin, muss ich mich gar nicht selber drum kümmern. Copy, das ist dieser Punkt, wo jetzt irgendwo mal Dateien ranwandern. In dem Fall von meinem ausführenden Verzeichnis, also wo auch immer dieses Docker-Bild gerade passiert und sein Bildverzeichnis hat. Da liegen irgendwelche Dateien drin und schmeißt die mir mal bitte nach App. Ah, okay, dann bauen wir anscheinend. Also ist da scheinbar, gehen wir mal von aus, dass da irgendwie ein Make-File mit dabei war. Cool, dann bauen wir. Ja gut, und jetzt haben wir gebaut. Und die ganzen Cache-Daten brauchen wir jetzt unbedingt nicht. Ja, dann löschen wir sie nochmal. Und dann zum Ende. Ja, was passiert denn, wenn jetzt wer den Container startet? Hat das irgendwie einen Standardbefehl? Ja, hat's. Das soll mit Python bitte meine gebaute App machen. Man kann es sich auch.
Because when I used to make spec files regularly, the only way to from something was to go find the Git repo and copy the spec file and paste it in a new repo. And that was how we did from back in the day. It worked for Jenkins, it worked for RPMs and deb files, and from was you had to know the best source repo to then copy it from. And putting that as a first line in a Docker file lets you skip all that. You can find the best version that you want to use by just knowing the name of the image you want to use. And layering on top what it is that you wanted to do. You can't do that with RPMs and debs. Like I can extract an RPM, I can then go in the file system and modify my files, and that was literally like the workflow of config management. Right? Like install the package, layer the stuff, start the service. And that whole life cycle got collapsed into Docker. It got collapsed into containers, where I don't need to do those 3 steps anymore. I don't need those 3 things. I can do it with one thing. And that's super powerful. And those layers, that from is just, obviously, like you have your file system again. And this is similar to what we were doing with deb files. And it's like, well, this is a file system. Again, you can do it from scratch and just throw your single binary in there. And the first time I saw someone putting a
containers come from. Because if they did that, I could tell them that Docker files where they come from. So a Docker file should not be confused with a Docker image. The Docker image are where your bits go. It's the binary representation of your app, okay? The Docker file is a set of instructions for creating a Docker image. So just like if you were building a C binary and you were using make, you create a make file that describes how that is compiled and linked, and the output of running make is an a.out binary or whatever you name it, right? Think of the Docker file as exactly the same thing as a make file, except instead of C source code going in and a binary coming out, it's this set of instructions that are going to run, and the container image is what comes out the end. So all Docker files extend from a base image, either Scratch or one of the environments I mentioned before. When the Docker file is built, the end you get a container image, and this is an imperative design, not a declarative design. So you're going to provide the exact instructions. They look like this.
We'll start with the development of a Python service, and we'll see how to add the other components later. So a good way to structure the project files is to have a per service directory. So we create a directory called app for our Flask service in this case. We then write a simple server that returns a hello message. And aside from the Python code, we have to create also a file with the required dependencies for our service. In this case, we need to install the Flask framework. Now, in order to run this simple Python application, we need a Python interpreter and, of course, to install the dependencies. So we could do this in a classical way by installing the Python interpreter and the dependency on our local environment. But this means we would pollute our standard dev environment, and we want to avoid this. So using containers to run it, however, would help us to do this easily. Therefore, let's have a look how can we easily containerize it. So to do this, we need to understand how do we get from the Python source code to the running container. The solution is to package our application as a Docker image, and then we can get our container with a simple Docker run. But how do we generate a Docker image in our case? Well, the only thing we need to do is create a Docker file which contains the instruction needed to build the image. The Docker file is then processed by a Docker builder, which will generate the Docker image. Then, doing a Docker run on that image, we'll get a container created and launched by executing that Python service. Let's have a look at the Docker file for our simple Python server. So just a reminder here that we'll cover mostly best practices that speed up the development time. If anyone interested in production-focused best practices, please check the blog post at the link on the bottom. That will cover this topic in more details. So to start with, this is how our Docker file looks like for our Hello World server. As you can observe, a Docker file is a text file containing instructions for assembling a Docker image. Each instruction or command is processed by the builder, and an image layer is generated from it. Let's go through some of this instruction now. So the first instruction will actually specify the base image on which we add new layers from our application. In this case, we decided to use a Python 3.8 image that should contain all the necessary standard tools inside so that we can easily run our Python program. We can change this base image according to what we are looking to do. For example, if we seek to generate a small image, we'd better check the Alpine tagged image that should contain a minimal install for Python. For other particular tags, better check the Docker Hub image page to find which one fits the case we are looking for. We discuss next the copy and run instructions. As we mentioned before, for each instruction in the Docker file, the Docker builder generates an image layer. What we forgot to mention is that the builder also caches the image layers that it generates. This means that if we make a change in one particular step, all the following layers are going to be generated again. The copy and run instructions are some commands that usually generate changes and, as a consequence, invalidate the cached layer. So we need to make sure we use them in an efficient way. For this particular case, we can see that we copy the dependencies files and then the source code. This is because the application dependencies do not change that frequently during development time, so we choose to install them before copying the source files that usually change frequently. It is highly recommended to add instructions for layers that do not update frequently before the ones that get frequent updates. This is in order to benefit from the cache mechanism, and this will speed up the build time for our application image. Finally, we copy the source files and specify the command to run the Flash server, and this will be the last image layer. So once we finished writing the Docker files, let's see how to run our Python server in the container. So we go in the project directory or the app directory, and we run the docker build command with the path to the Docker file. Next, we check the image with the tag specified in the build command is in the local store image, is in the local image store, and then we can start a container with Docker run with the generated image. This being done, we now containerized our Hello World server. So let's see how to add a new component to the project and how to wire it to our Python service. We're going to add a database service to the project, and for this we update our Python code with a database connection. This requires also to import the library needed to connect to a MySQL database and add it to the dependencies files. Once we've done that, we need to rebuild our Python application and run the container. But at this point, we need to start a database instance too. So how can we manage this in an efficient way? Well, here is where Docker Compose offers a very easy way of coordinating containers and spinning up and taking down services in our local environment. For this, all we need to do is write a compose file containing the configuration for our project services. Once we have it, we can get the project running with a single command. So let's see what is the structure of the compose file and how can we manage the DB service with it. This is the sample file for our Python service and the database. As you can see, we define a list of services, and in the DB section we specify the base image directly, as we don't have any particular configuration to apply for it. Meanwhile, for the Python service, it is going to have the image built from the Docker file. According to where we get the service image, we can either set the build or the image field in the compose file. If the build field is set, make sure it is a path with a Docker file inside. To initialize the database, we can pass environment variables with the DB name and password, while for our Python service, we map the container port to the local host in order to be able to access it as in the usual way. Now, let's see how to deploy our two-service project with Docker Compose. All we need to do now is to go to the project directory where we place the Docker Compose file and run Docker Compose up. Docker Compose is going to take care of pulling the MySQL image from Docker Hub and then launching the DB container, while for our Python service, it is building the image locally and then running the container from the built image. All this is triggered with only one command. So let's see now how to add the third and the last component to our project, the web UI service. As we did before, we create a dedicated folder as we have specific files for it, and we add the code and the Docker file to build its Docker image. So to be able to access it, as it is the front end for our project, we map the port 80 to localhost in the compose file. With a simple